she, with her problem that she did earlier tonight, doctor, what she did, she had an equation that she could figure out the angle of theta dot and the radius dot. She was able, and then she was able to take the second derivative of it and get the radius double dot and the theta double dot. And then she was able to use those to solve for velocity or acceleration, or the components of velocity and acceleration. So right now, we have the bits and pieces that we need to be able to solve for the components of velocity. Just looking at our PowerPoint for the velocity components, this is not going to help. Let's see. That is our cylindrical components in terms of velocity. Still writing it down? Or is it going fast? No, I'm not writing it down at all.
No, I did it.
You're okay? All right. All right, so I have some intermediate information. I've got my theta prime, I've got my r prime. Let's go back to what was being asked for. Radial velocity and transverse velocity. See if I can find. So did I skip over those functions? No, I did. I just wondered why they were not on this sheet. So that one that I deleted. Let's see if I can find it. That's from the last section, so that is not in here. So that was, I know what it was. I was going to put a slide in there and I didn't. So I missed a slide. Well, that's not right. Anyway, so the equation, in your book, the velocity, the radial velocity is going to be equal to the change in our radius. And what does that mean? Well, if we were going around a circular curve, the radius stays the same, right? If you're going around a circular curve, your radius stays the same. We're not. We're going around a spiral curve. So our radius continues to change the whole time. So we're either, in one direction, we're getting smaller and smaller radius, and the other direction, we're growing up. We're spiraling out. So my velocity, I actually have a radial velocity. I'm either coming toward the middle or toward the center, or I'm going further away. I actually do have a velocity along the radial line. The previous problem, that was not true. The previous problem, they were going around a circular curve. So the radial velocity would be 0. You're not getting closer or farther away at all. However, you do have a tangential velocity. You're going along the curve, right? That's what makes this spiral wild, is because you've got a velocity, a radial velocity. So there is a change of radial. And that, it just happens to be exactly the same of what we calculated. The derivative of the radius function is, of course, going to be the velocity along that radius. The second derivative would be the acceleration change along that, radius line. So, and then, I didn't state it. Doesn't say equation. How did they Maybe they stated it in one line.
They're both in one.
They're both on one line? Okay. So one of them is the angular velocity change, and then one of them is the radial velocity change along the radius. And then we're talking about cylindrical components. So cylindrical components have a radial distance and then it has an angular change, or angle, right? So radial distance, angle change, and z up. We're still looking at a 2D problem, we're not even bothering to do z. So the angular velocity is going to be effectively, that's the tangential velocity at instant, is equal to the change in angular velocity, or actually that's just angular velocity at this instant, sorry, the change in angle, that's what that would be, it's the first derivative. So I'm going to angle function, take the first derivative, and that's the change in the angular velocity. Take the second derivative, and it would be the angular acceleration. Okay, it's tough stuff, actually. Okay, the velocity of the angle change is going to be equal to my radius. How far am I out? Very similar to what I talked about earlier tonight. So the how far am I out would tell me what my velocity would be, tangential velocity would be. And that radius equation goes all the way back to what they gave us. They gave us the radius is changing, how far out we are changes by 1,000 divided by whatever my angle is. So I plugged in 1,000 divided by my angle is equal to, well, we happen to have that solved. That is your angle dot, angular velocity of 0.14. And then I plugged in the angle. They wanted at an angle of 9 pi over 4 is when we're trying to solve for all these things. And there is basically your tangential velocity is 19.8 meters per second. Right at this instant, as we're going along the spiral curve, and we've gone all the way around at another 45 degrees, our velocity, and it's minus, so that means we're actually going inward. Our velocity inward is 2.8 meters per second. Every second we're going 2.8 meters closer to the center. And then at this instant, our tangential velocity, kind of sideways velocity, right, is 19.8 meters per second. Wow.
Can you scroll down just a little bit? Or up? Yeah. That VR equals, okay, so velocity, radius, right? Radial velocity equals the derivative of r, the first derivative of r? So I don't quite understand.
You've got a radial line, and you have an equation for that radial line. So the distance that you're radially away from the center is the equation.
That's your position equation then?
Position equation.
Okay.
But that's exactly right. It's your position equation, but it's a weird position equation because it's only with respect to the center point. It's how close you are to the center point.
Okay.
So that the distance from your center point is equal to that equation. The first derivative would be the change in that distance, so velocity, what the velocity is along that radius. The second derivative would be the acceleration along that radius. But the weird thing about cylindrical coordinates is that we're just talking about the radial line. You could actually be spinning around that radial line, and you could have an inward or outward velocity and acceleration, right? So that equation is only describing along a radial line. That radial line might be swinging around the whole time, but along that radial line, it's doing something like this. Either, in this case, our velocity is negative, so it's going toward the center. Even though we're spinning around, we're coming toward the center. That's why this is a spiral. And that's why this is a wild
Can you
cone.
go up this a little farther?
Too many dots.
Hmm?
Too many dots.
Too many dots, yeah. Too many dots and funny symbols.
Well, it's dynamics.
You just have to go slow.
That's right.
That's the thing. Not you right now, I'm just saying like when you're doing it, you can't,
I should probably go slow too.
oh man,
Yeah.
yeah.
So could we, for some, could we say, if we represented the, first derivative of, the first derivative of R,
Okay.
could we represent that in a different way? A D over, what, dr over something, what it's respected to,
Yeah,
or,
it's with respect to time, so it would be dr.
so
dt.
we could say VR equals
V,
velocity radius, or, right, velocity radius.
and then you would take the second derivative of the r to get the acceleration. So the first derivative of the r, so dr dt, would
So-
get you velocity along the radial line. The second derivative, so dr, double dot basically, dr to, well, second derivative, dr second derivative to, with respect to time.
Okay, so we
gets
would
you
say-
acceleration.
We would say R dot equals VR over DT, right? Is that right?
No.
Because you would use your position? You're taking the derivative of your position? No?
Because
Right.
those are different. When you say dr dt, that's the first derivative of r,
Of R.
and that is not acceleration. First derivative of r is velocity.
But velocity rate, the VR is
If you
throwing me
take-
off.
If you take the first derivative of velocity, you would get.
You'll get acceleration.
Yeah.
Yeah,
But
I
how you
get that. I
describe
just,
that-
the VR is confusing me. And I know you explained it, and I understand when you're explaining it, but then when I look at it, I don't really quite.
And that is why Newton simplified it by just putting a dot above it. So we've got, so let's just say you have your radius function, whatever that animal is. And if we take the first derivative, dot, that would be the same as basically a dr dt. The dot specifically means with respect to time.
That's right.
It was basically Newton's
Mhm.
simplicity. He just said, you know what, you put a dot above it, and it means it's with respect to time. So I'm going to take my radial equation, take the first derivative of it, and now I have velocity along that radial line. So you've got a radial line, let's say R, we're going to call that R. This positional equation, if we take the first derivative of it, we're discovering what our velocity, in our case, our velocity happens to be negative, minus 2.8 meters per second. And that's coming in on this line. If we took the second derivative of it, we would get an acceleration in, I don't know, we didn't bother to do the second derivative, but it would be a acceleration along that line. And what's interesting about cylindrical coordinates is you could actually be spinning around that whole time, but you gotta just kind of isolate and just think about what's my distance, my radial distance as I'm moving inward. Let's see if I can do this, a spiral. I tried. So your rate, as we keep coming inward as we're spinning, and the velocity of the inward is equal to dr dt. The second derivative, so that would be d, do they put like 2 or something like that? dt, something like
Yeah,
that?
I think so.
The second derivative, that would be your acceleration along that radial line. And of course, the radial line could be spinning. Because that spin is angular stuff. So we're ignoring that, and we're just talking about this. Because the angle is how, what's your rate of your angle change? That's this theta stuff that we were messing around with tonight. So like the theta is your equation, whatever it be, your equation of your angle change is theta. So if you take the first derivative of it, that's going to be what, d theta dt. So that's the change in angle with respect to time, which would be angular velocity. That's angular velocity. And if I take the second derivative of my angle equation, I've got my angular acceleration. How fast I'm continuing, either I'm speeding up with my spin or I'm slowing down with my spin. Angular acceleration. acceleration. And the cool thing about the little dot and double dot is it always is with respect to t, so we don't need to do something else.
Okay.
So I hear what you're saying. You're saying, oh, I want to call this velocity, and I want to take the derivative of velocity, but that's kind of complicated if you add that extra thing in. Say first derivative is velocity, second derivative is acceleration.
But when you put VR, that's just saying the position of,
This is saying that you're doing this with respect to the original equation, the radius equation. Took the first derivative with respect to the original equation, take the second derivative with respect to the original radial equation. You're keeping, in the terms, you're keeping what your original was. Because if you change them, I think it's going to throw you.
okay,
Keep changing them as you go.
thank you.
Yeah. Oh, that definitely is. Good stuff. All right. Next time we get together, it's going to be back to Newton's laws. Back to Newton's laws. Working power, energy, momentum, impacts, that kind of stuff. Which we did cover in engineering physics, but we're seeing it again with a higher level of math, clearly. All right. That's okay. I'm going over it with you guys. It's a team effort. All right. Well, we'll pick it up next